Oh. All right. So our fifth speaker for the session is a good friend of mine, Jordan Budhu, from Virginia Tech University, and he's going to be presenting his work in collaboration with Steve Ellingston and Michael Brewery, as well as Sean Hum, on loading rims of radio telescopes with reconfigurable reflectarrays for adaptive null steering.
All right, thank you, Cody. Thank you for an invitation to the special session. I appreciate that. Here I'm presenting to a different kind of application for maybe reconfigurable intelligence services that you may not have thought of, but it's in collaboration with my colleague Steve Ellingston and Michael Brewer at Virginia Tech, and also in collaboration with Sean Victor Hum at the University of Toronto. Here today, I want to talk to you about loading rims of radio telescopes with reconfigurable reflectarrays for adaptive null steering. So what is the big problem that we're facing now? We have radio telescopes that are trying to do science for astronomical sciences, and we're loading more and more satellites up into space, low Earth orbit satellites, which are now like part of Starlink, for example, covering the Earth with radiation. And the problem is that these satellites can then cause some kind of interference that's passed into the aperture of a radio telescope. And there are multiple reasons why it's caused a severe threat to radio astronomy. For example, radio signals arriving on Earth from astronomical objects are very weak. So they're easily swamped by terrestrial sources of interference or signals that are coming from satellites that are orbiting around the Earth. And these weak interfering signals can contaminate the data collected by radio telescopes, leading to erroneous conclusions about data that they're collecting. Furthermore, frequencies allocated on a primary basis to satellite constellations are adjacent to frequencies that are allocated for radio astronomy. And that can be a problem, for example, if you need to observe outside of your allocated band, for example, redshifted observations, or if you need to examine broadband continuum observations with pulsars and so forth. So it's definitely a problem with radio astronomy, these rise of mega constellations, Iridium, Starlink, and so forth. So there's a big push to try to come up with technologies that allow coexistence of this spectrum, and this is one such idea. So what is our solution? The concept is here on this slide. We have an existing radio telescope, and we're going to outfit the radio telescope's parabolic reflector with a reconfigurable reflectarray that exists only along the outer rim of the reflector. And for example, here, you would have a reflectarray, which is only 6 unit cells deep, that covers the entire rim of the reflector antenna. And the ground plane of this reflectarray is the actual reflector there. So you can picture, you can kind of wallpaper it into the rim of the reflector antenna. What does that do? What does that give us the capability to do? Well, if you first plot the pattern due to the reflector portion only. So the radiation pattern of the radio telescope is shown in this red curve here. And say I want to drive a null for a satellite that's overhead, that's passing overhead in low Earth orbit, and I want to null its signal coming into the aperture of the radio telescope. So I need to track the satellite with a null, and I can do that by reconfiguring this reflectarray such that it drives its maximum, say this black pattern is due to the reflectarray, at the null angle, but it's 180 degrees out of phase. So when you superimpose by phasor summation the signal due to the reflector and this reflectarray, it actually cancels and drives a deep null at the angle of interest. So that's the idea, and it's also able to interface with existing radio telescope infrastructure. Okay, so this concept is first introduced in a seminal paper by Steve Ellingston and his student Ramanika Sengupta. They came up with the idea. In this work, they used impulse currents to work out the idea and its feasibility. And then it was explored a little bit further in one of my other colleagues, Sean Victor Hum, where he designed a parabolic reflectarray with a reflector, or sorry, a parabolic reflector with a reflectarray around the rim. But in his case here, this is a planar construction. It is not conformal to the reflectarray, which in some cases might be easier to deploy. And it used fixed non-reconfigurable unit cells. So in this work, we're going to go a little bit step further, make it a reconfigurable reflectarray and drive nulls at different angles dynamically. The similar concept appears in this work by Scissors. I want to mention it. But there are some advantages of our work over theirs, where they utilize some kind of RIS that they place outside of the reflector on the ground near it. And they're able to sort of measure the interference and conjugate it and send it back into the aperture along with the signal coming in. And they can cancel it that way. But our approach has a lot of advantages over that. So how are we going to design this reflector? First off, it's conformal, and it exists only along and outside of a parabolic reflector antenna. So the idea we came up with to design it is the following. in physical optics, you commonly use, so in physical optics, the approximation usage, you replace the geometry at the point of reflection with a local tangent plane, which is infinite, right? And then you calculate the induced surface current, assuming that the entire geometry is this infinite plane. So we're gonna use the same idea here to calculate or to design the reflector array, except we're gonna replace at the point of reflection, the parabolic reflector with an infinite doubly periodic reflector array. And that's very easy to calculate the reflection dyads from. So it's a kind of a double whammy. So the approximations that are used in this approach are local periodicity, right? You assume the reflector is embedded in an infinite array of like elements, and we use that approximation to characterize each of the unit cells. Furthermore, the tangent plane approximation is assuming that at the point of reflection, the geometry is planar. Of course, it's curved. And another approximation that there are negligible effects of truncation at the edges of this paraboloidal annulus shaped reflector array. So these three approximations we had to characterize at first before we were able to move forward and to validate this tangent plane approximation. One other good thing about tangent plane approximation is the local coordinate system of that tangent plane, right? So if the local coordinate system of the tangent plane that we put there is always erected in this manner, then the local angles of incidence to each patch in the reflector array is always identical, which is good because in order to calculate the reflection dyadic from a given reflector array unit cell, it's a function of the incident angles, the local incident angles. But the benefit of having this local coordinate system approximation, of course, the theta angle doesn't vary much because these are only over 1.5 degrees of some tangent angle where the reflector exists, but it's always at the same azimuthal angle of 180 degrees. So you characterize your unit cell once at one angle of incidence, and you can use that reflection dyad for the whole entire reflector array. So that's one benefit of it. Here's a geometry. We have a reflector of diameter d, and we have a reflector array that we put along the outside of the reflector that has a diameter of d minus d naught. So the new reflector has diameter d naught, and that will impact the gain of the original reflector. But we've chosen it such that we don't impact the main reflector's gain by more than a couple tenths of dB, right? And you can actually adjust that depending on the needs for your angular range of side lobes that you want to know. Very good. So this is all classical formulas that I'm sure you're familiar with. We have a reflector parameterization, the classical way using secant squared of theta, draws this curve here. You can rotate that in azimuth to generate the paraboloid. We have the subtended angle based on the f over d, and the normal unit vector here given in rectangular coordinates of x global, y global, z global. And that's normal to the tangent plane as well, right? That we place at the point of reflection. We're using a raised cosine q feed model here. And in order to y polarized rather, the value of q, of course, tapers your feed and allows you to adjust your spillover and taper efficiency ratios. And this value of q here can be calculated given your desired edge illumination in order to get the efficiency that you want. For us, we're doing an 18-meter reflector example with an f over d of 0.4 and a subtended angle of 64 degrees. We set the q value to 1.14. So once we have the incident field, we need to now calculate the scattered field reflected from the reflector plus reflector array. And the way we do that is, of course, using the classical formula, the radiation integral, where we do the spatial convolution of the surface current density on the reflector with the Green's function. And in paraboloid, or in the parameterization of the paraboloid, it looks like this. And once we've calculated the scattered field in spherical coordinates or spherical components, we use the Ludwig's third definition to get colon crosspole patterns, electric field. And then we can calculate the radiation intensity. We can approximate the radiated power by that power intercepted by the cosine q feed and the reflector. And then from there, we can easily calculate the colon crosspole radiation patterns, or directivity patterns rather. Okay, so the last step is we need the current to put into that radiation integral, right? So how do we approximate the current? The induced current is approximated using physical optics, commonly done for reflector antennas. We have 2n cross hi or 2n cross hr. And we can represent the reflected magnetic field in terms of r cross with e over eta. And we know what the r is for the reflected field because a parabola's unique property, geometric property, is all rays exit parallel along the axis of symmetry. So that means r is always minus zg, or z global, minus z hat. And of course, we can represent the reflected field in terms of reflection dyad dotted with the incident field. And this is a key kind of step to represent the current, because now we can use this same kind of radiation apparatus to calculate the radiated field from different types of structures that might appear on our reconfigurable reflector. For the perfectly conducting plane, part of the parabolic reflector, we use -I because it's perfectly reflecting. And then for reconfigurable unit cells, we just do an locally periodic unit cell approximation simulation in CST Microwave Studio for 1-beat phase shifting unit cell. I'll show you in the next slide, and we can get the reflection dyad from that. Or for fixed non-reconfigurable variable patch size based unit cells, we can vary dimensions of a patch. So the reconfigurable unit cell that we chose here is a patch antenna square, so we can maintain isotropy. We have 2 pin diodes here that are Skyworks SMP 1320-040LF, and with the diode parameters shown here. They're pin diode switches, so when both switches are on, we shunt the current to the ground plane layer to these 2 vias. And when the switches are off, we allow the patch to resonate in its natural resonance. Below this sort of ground plane here, we have a biasing layer, which has a radial fan to choke the RF and a DC bias line. So both these switches are always operated simultaneous to maintain isotropy. We don't want to disrupt the polarization. We use CST Microwave Studio for this reconfigurable unit cell, and we calculate the scattering parameters, which are components of this reflection dyad, at different frequencies for 2 states of the switch, on and off. So we have theta theta, theta phi, phi theta, and phi phi. And we show both the phase in blue and the amplitude in red, the dash curves associated with the off state and the solid curves associated with the on state. So the important thing to draw from this is we get 180 phase degree shift between the on state and the off state at the frequency of interest, which is 1.5 gigahertz, and therefore creating a 1-bit reconfigurability. And we also do it with less than 0.4 dB of switch loss. We'll see that switch loss is really not a factor for us, though, which is one key benefit or characteristic of our design or our approach. Okay, so non-reconfigurable reflector unit cells, we just use a spectral domain method of moment code that was kind of pioneered by David Pozar in his seminal paper, or we use CST Microwave Studio, you get the same result. So you can just vary L, the length of the patch, and it's a square patch, and you can get these phase curves, which are the angle contribution to the reflection dyad. Okay, as I was talking about with the calculation of with the radiation efficiency, because this reflector is placed along the outer rim of the reflector, which is weakly illuminated anyhow, right? You normally illuminate this 11 dB down with respect to the center. So all the lossy material that you would place in this system is weakly illuminated. So if you calculate the contribution due to these losses, you can do it in this way. Radiation efficiency is the sum of the power after reflection divided by the power before reflection. So what we do is we calculate the reflected field. Our total, remember, has all of the switch loss, the conductor loss, the dielectric loss embedded into it because it doesn't have a unit amplitude. You sum over all reflection dyads, which include the -I due to the perfect conductor, and all of the reflection dyads associated with the reconfigurable unit cells, and you divide that by the total power before reflection. And what we find is we get 99%, right? These are weakly illuminated. Most of the power is going in here, right? Very little power going to the edge. It's sufficient power for us to derive a null in the side lobe in order to drive a null in the side lobe span. So that's useful. Anyhow, we can calculate the gain then if we have the aperture efficiency where we load this this radiation efficiency in with the spillover and taper efficiency. Okay, good. So how do we determine the switch states if we want to place a null in a particular angle? We use an approach called serial search, which showed up in this paper first. And the way we do that is first we calculate, say this is the null angle here. We first calculate the radiation pattern due to the reflector portion of the entire reconfigurable reflector array and reflector system. What we get there is sort of this red curve here, right? This is the pattern due to the reflector portion of the system. And then we start with the first patch in the reflector array. We calculate the pattern in the null direction, say this patch. Calculate the pattern from that patch at this angle by reflecting the incident field off of this with its own reflection dyad. And we do that for both switch states, on and off of this reconfigurable unit cell. Then we keep the switch states, which reduces the copole magnitude at that null angle, right? We want all of these switches to bring down the reflector pattern at the null angle, right? So we keep the switch state that starts to reduce it. We add that total to the total field amplitude there, and we keep going around. Check the next patch, which switch state reduces the total field at that angle. And we do that so far for all of these patches. That's why it's called serial search. We check them one at a time. And the third patch, of course. Okay, so here's some results. The first result we're going to show is a 18-meter reflector that has original directivity of 48.38 dB. We're going to null at the angle 1.75 degrees, which is in the second side lobe peak of the original reflector pattern. And here are the switch states that we come up with the serial search approach. So blue is on and yellow is off. And we can see we come up with a switch state for each of these reconfigurable unit cells, and it drives a null directly at the intended angle. So there are a couple patterns here that are shown. The red is the original 18-meter reflector without the reconfigurable reflector array placed around the rim for reference. And then we have the fixed reflector array that we use to validate all these approximations that we're making when we design the reflector array, tangent plane and the curved surface, but becomes planar and so forth. And what we see with that black dash pattern is, and of course, this black dash pattern is also obtained with a full wave simulation of an 18-meter reflector with this reflector around it on a giant computer. And it shows that we do get the nulling with the fixed reflector array, right? And then with the reconfigurable metasurface, which is called, or reconfigurable reflector array, which is called the interference mitigation system, we get the pattern that's shown in blue. What we can see is by reallocating part of the rim for reconfiguration purposes, we lose a couple tenths of a dB here, but we're able to reconfigure the reflector array to drive a null at any angle that we want. We can do that dynamically, right, and fast enough to track satellites in the sky. Here's another example where we null at a new phi angle 30 degrees and at a new theta angle 1.18 degrees, which is the first side lobe peak in the original reflector pattern. And this example has the switch states shown here, and we can see that we're able to achieve even nulling of the first side lobe. So we can null anywhere, and we can move that null with the satellite. So in conclusion, we developed a reflector array that we placed along the rim of a reflector. We interfaced that to the existing hardware for radio telescopes. We're able to reconfigure the radiation pattern of this now reconfigurable adorned reflector in order to place null anywhere we want in the side lobe span, even the first side lobe to any of the other side lobes. We can track the satellite and null its contribution to the aperture field. And we did it at two angles here just for demonstration. One of the main contributions or takeaways is our approach has very good radiation efficiency. All these lossy materials are weakly illuminated and don't contribute much to the overall power loss with respect to the total power in the feed. I would like to acknowledge the National Science Foundation for their support in this program through this grant, AST 212-8506. And all of the work that's been done in this area at Virginia Tech is nicely tabulated in a website that you can visit here if you're interested in this topic. There's a lot of work here that was done prior to this, and things that we will be doing in the future will be placed on this website. So it's a place to maintain all the results. And with that, I would like to thank you guys for your attention.
All right, so some questions, start with John.
Okay.
Yeah, that's really nice. I like the concept. I was interested to see at the very end, you showed the rim and phase states. So we have big swaths of yellow and blue, right?
Yes.
So thinking about practical implementation of however many tens of thousands of unit cells that would be to go around the rim of a big reflector. Have you thought about other methods of doing this other than pin diodes in half lamp